have Katharine Mach join us today. I'm going to share a little bit of her background with you as I introduce her. Katharine Mach is a senior research scientist at Stanford University and a visiting investigator at the Carnegie Institute for Science. She leads the Stanford Environment Assessment Facility. Advancing foundations for action, her research is focused on intensive assessment of climate change, risks, and response options. The goal is innovative in evaluating new approaches for assessment, simultaneously applying with them to inform decisions on policy. From 2010 to 2015, she directed the scientific activities of the Working Group 2 of the Intergovernmental Panel on Climate Change, and focused on impacts of adaptation and vulnerability. The work culminated in IPCC's 5th assessment report and its special report on managing the risk of extreme events and disasters in advance of climate change adaptation. Dr. Mach received her PhD from Stanford University, and she has a degree from Harvard. She's going to make a 10 minutes presentation on adaptation, but because of her general background and expertise in climate science, we look forward to entertaining any questions that you may have. I have some C questions to get started, but I think being able to complement, we're doing at CCL with the state of the science is a real treat for us. Anyway, please welcome Dr. Katharine Mach.
Great. Thank you, Dave, for that introduction. And as he described, we're really going to drive most of the conversation today by your questions and Dave's questions. But I'm going to start with a little primer on how science has advanced rapidly in this question of, is this global warming? Fill in the blank. Is this drought global warming? Is this heat event global warming? Is this wildfire global warming? That question has been coming up again and again over the last year, a year in which the US saw $300 billion in damages from extreme weather and climate events. So first, we'll take this question, was this specific event global warming? And we'll do a little bit of a tour of history. So if you jump back 2 decades, but really even if you just jump back 1 decade ago, the scientific bottom line was that you couldn't link any one event to climate change. Fundamentally, scientifically, we had a difference between weather and climate, and we couldn't specifically make that bridge. Jump forward to today, though, and it's incredibly different. In terms of our analytical capabilities, we can tease out the role of our emissions of heat-trapping gases event by event, and that role generally ranges from a component of 0 to 100% of the likelihood or the magnitude of the event being due to climate change. Why is that the case? First, I'll start with just a bit of a description of the relationship between average climates, how the climate is changing in aggregate overall, and what's happening with extremes. So in this plot, which I think I can access with the laser, there we go. This is our mean temperature, let's say, of the planet. Now in our warmed world, it has shifted over to this dotted distribution. We've had a 1 degree Celsius temperature increase on average. But in terms of where the rubber hits the road, and you see the sharp end of the climate system, it's not really in the average temperature we experience, it's in the nature of extremes and how they're shifting. And so as you shift that average global temperature increase, the action in terms of impacts people experience is often over here. So what do we know about how these extremes are changing? First of all, we can look at them in aggregate, and we see very strong evidence that overall, the likelihood of extreme heat events has gone up, basically anywhere you look. But it's also the case that whether you look at heavy rain, a greater fraction of rainfall overall is falling in these heavy rain events. It's a very clear trend around the world. But also in terms of coastal flooding, for example, where in almost every place you look, storms heading onto shore are acting on top of sea level rise. But that jump from a decade or two ago to the present means that we can now make these same types of statements for specific events, whether it's the drought, and I'll walk you through that one in particular. Things like Superstorm Sandy, where it was landing onshore in New York City in October of 2012 on top of 1 foot of sea level rise that has happened there. You can say the same thing for heat waves, especially the damaging 2003 heat wave in Europe, or for droughts, even the drought in Syria. Although if you ask political scientists, is that a climate war? They will say no, but there is some role of how climate is changing in that area. There are 2 different major ways that this single event extreme attribution happens in the science. Number 1, you look at observations overall, statistically, and you determine the likelihood of events in the past and how they're shifting through time. I'll walk you through an example like that. The second major way that we attribute the role of climate change in individual extreme events is that we run a model with our emissions of heat-trapping gases, and then we run the model again without our emissions of heat-trapping gases, and we compare the probability of those specific events across the 2 scenarios and determine the fraction of attributable risk. You can do this for events overall, a heat wave overall, or you can do it for specific ingredients and components. So for example, the fact that Superstorm Sandy was having an ingredient of sea level rise in the overall magnitude of risk. For something like Harvey, which was an incredibly complex event, it comes down to the temperature of the water offshore, the depth of that heated water, how much more water can be held in the atmosphere, and then also the atmospheric blocking that can happen. You can do that single event attribution for each of those components, as well as for the event overall. So what does that first category look like when you say, how are observed trends changing through time? Here I'll walk you through Noah Diffenbaugh's analysis. He's a professor at Stanford of the California drought. This is going to be a little technical, so bear with me. So what we're looking at here is a plot of what California climate has been like on the observed record, 1896 to 2014, the time when this study was done. On the vertical axis, it's showing whether each individual year was hotter than normal or cooler than normal. And then on the horizontal axis here, we're looking at whether the year was wetter than normal or drier than normal. Each dot is a year. Then on this additional color gradient, we're seeing whether drought occurred or not. And the key point here is that the likelihood of drought is highest when it is both hot and dry. Both hot and dry. Jump forward to the present, and now we make this type of comparison of the last 2 decades. And what we see is that we haven't actually seen that big of a trend in the precipitation in the state, but it is a lot hotter. And the fact that it is driving temperatures up this way on the on the vertical axis, it means that we have a much higher likelihood of drought in the state, because when we do have a dry year, it is much more likely to also be a hot year. This type of observational analysis is being run routinely now for many different types of events, and we can talk about that in the question and answer. I'll just give one final example of how the alternative approach pans out. So first of all, here we're thinking about changes in climate overall. These are these global model climate experiments where you're running the models with emissions of heat-trapping gases and then without emissions of heat-trapping gases. You can do this for the globe as a whole, for example. Here's running the model in the red here with our emissions of heat-trapping gases. Take out emissions of heat-trapping gases and the model simulated temperature like this, and the black is what has been observed. Same goes for California. These are some of the major ways that we understand aggregate changes. But you can take these types of approaches and now drive them forward for extremes. And again, work by Noah and his group has showed that most of the record heat occurring across the planet is exacerbated by our emissions of heat-trapping gases, and we can say the same for precipitation and drought for about 50% of the surface. In terms of all of the extremes that happened in the last year, analyses are ongoing. The first analysis of Harvey was published just a few months after that event, and there are many different research groups who are looking at the conditions that exacerbated wildfire risk throughout the state of California, in the Bay Area here, but also further south. So from here on out, we're going to drive it by questions, so I will sit with Dave.
Thank you. So I'm hoping that you're thinking of a good question that's always been nagging you about climate science, but I'll start one off as one of mine. It goes like this. The special report of the IPCC on managing risk and events assessed exposure and vulnerability in framing policy to reduce climate change risk. However, many climate skeptics are attributing these factors and discounting human cause of climate change, i.e. people in the wrong places, etc. Is there any work that you're aware of seeking to quantitatively parse out the former from the latter?
Great. So when you think about risk in a changing climate, the key thing is that the risks of climate change are not just due to climate change. It's how climate change intersects with societies and ecosystems. So on the climate side of risk, you've got the hazards, everything I was just talking about, the heat waves, the droughts, the floods. But those events in isolation aren't enough to give you damages that matter. It's how those hazards intersect with the vulnerability and exposure of people and societies. So oftentimes in the climate narrative, there's this bifurcation of experiences with climate change, where oftentimes there's a pointing to developing countries globally and saying that's where vulnerability is highest. It is often exceptionally high there, but I think it's equally important to realize that wealth is not necessarily protection, and the exposure of assets can be profound. So Sandy or Harvey, these types of events carry very large damages, not only because of the hazard, but because so much is exposed. So in terms of the science of attributing disaster losses to human emissions of heat-trapping gases, that's really the challenge. You have to tease out how has the climate been changing from how is society changing. I think some of the most powerful evidence on the hazard side is really what I just talked about, the fact that we can go hazard by hazard and really see how we're driving up the odds just on the basis of those hazards. At the same time, that to really understand analysis of damages through time, you've got to pull out how much more stuff that can be damaged is in the way of harm. And people flood the coast through the course of human history. So we have built up expensive, valuable things right on coastlines, for example, that are increasingly exposed. And some of the single event attribution work now is just starting to step through that whole chain of damage, essentially doing daisy chain linkages of models to get all the way from what was the likelihood of the rainfall that contributed to a flood event, and then how did that ramify through this full suite of linkages that give you economic damages?
Question from the audience.
Just use this one.
Let's try that.
Hi. Very interesting. I actually like, I think to emphasize, this is really important. I've been a risk assessor for like 40 years, and mainly in human health and other areas, but the vulnerability hazard is so important across, and I think an analogy that might make it clear to people who don't understand climate is like with earthquakes. California has a much higher hazard, but our vulnerability is often lower because we're so prepared. You know, we reduce our vulnerability. Boston has a hazard of earthquakes. It's lower than California, but the vulnerability is enormous because they don't do the strengthening that we do. So my question is more on communication. This is very difficult to really communicate to general audiences. And I guess my fear is, how do you take this and present it to people who are saying things like, how could this be climate change? It's so cold this winter. And this is what we get. I mean, you know, you go out and if you're a scientist, you look at the data, you say, you know, the temperatures, and then there's an anomaly the other way, which actually is probably attributable to climate change because the vortex is changing. But again, I'm really struggling with how do we offset that, because that sells on all kinds of things, Fox News and everything else, where they say, these fools, you know, they told us the climate is warming in New Orleans was shut down for 5 days because of ice and cold. So anyway, just kind of a thought. I don't know if it's yours to answer or just a broader question.
So where I start in cases like that is the fact that responding to climate change is a way to build a better world, full stop. I think oftentimes the science on climate change is contested not because people disbelieve science or engineering or medicine and any other aspect of their lives. It's really discomfort with the responses. And yes, you can importantly emphasize that we have robust understanding that the climate is warming. The last few years have been absolute record breakers. Most years over the past 2 decades have been the absolute warmest that we've seen. We're now seeing things that are beyond human historical experience with the climate in aggregate, in specifics. So I think you can point to the unequivocal fact that the climate is warming and that we are seeing that play out, but sometimes I think just not even starting there, but saying the top 5 producing states of wind power in the US voted red in the last election. We see the fact that, I think your earthquake example was a beautiful one. In Florida, they talk about not the fact that they have sea level rise, but they've got a flooding issue, and they know they have a flooding issue. So I think in many different places, just forgetting the science of the physical science basis of climate change and starting in where people care about their lives and their jobs and their security and their well-being can be a more effective starting place, somewhat just dismissing the loud caucus and ruckus around whether it's happening or not.
Yeah. So this question is not really about how to convince people. Let's assume that people are familiar with the science as we understand it, and they get it, and they say, yeah, we have really screwed up. It looks really bad. And not just today, but it's going to continue because we've set something in motion that has a lot of momentum to it, this warming climate. And then they say, so realistically, can we recover? And how quickly, and which levers do we pull to recover fastest? That is, well, eliminating all fossil fuels from automobiles, what's the marginal utility of that in restoring a healthy climate? Or do we have to go to methane? How dramatically do we need to change in order to restore a healthy climate? And have you or other scientists looked at the marginal utility of different kinds of remediation to answer the question of, is it too late? And if not, where do we begin and why?
Great, so I think a simple place to start there is the fact that our emissions of carbon dioxide have near permanent warming associated with them. So maybe as many of you know, long-lived greenhouse gases are fundamentally different from things like air pollutants that we commonly experience. So when we put carbon dioxide into the atmosphere, as it slowly drops in concentration through time, the oceans become less able to take up heat, giving us this near permanent warming. So when we think about stabilizing the temperature of the planet, which we need to do unless we want to achieve something that's wildly outside of what the planet has ever experienced, we need to achieve a land use and energy system globally that is at zero emissions of the long-lived forcers, CO2 most especially, and at constant emissions of the short-lived forcers like methane. And shifting to a net zero emission system is really not a question of if, but when. And when is very strongly correlated with what temperature the global stabilization happens at. So something like a 2 degrees Celsius temperature stabilization for the planet, about twice as much warming as we've seen to date, would necessitate zero emissions at the global scale in the second half of this century. But even if we say, okay, 4 degrees Celsius, that takes us far out of our human experience with the climate system, but it's something that could be possible. This near zero endgame energy system there would need to be achieved not that far into the next century. So for a lot of this, the questions of costs are actually really about unknowables, the fact that if we get to the point where clean energy is the good stuff on the basis of costs alone, that innovation curve really starts to drive itself towards deep decarbonization, even though the last third of emissions, say, will really require grappling with the hard-to-reduce sectors, for example, industry around cement or steel, or long-distance transport, aviation, for example.
I'm sorry, I have a rather specific question. I'm from a rural county, YOLO. We produce a lot of nuts. 90% of the world's almonds come from California, similar percentage of pistachios and so on. We also have a problem in convincing people climate change is real and important to them. Cooling hours determine how much crop you get once you've planted trees, and people are planting trees all over the place. Do you have information on changes in cooling hours? I think it'd be very important convincing farmers they pay attention.
Yes, those types of data are definitely available, and if you wanted California-specific values, I could point you to some resources. Basically, we're seeing a substantial increase in cold nights, increase in the temperature at night, so you're losing the cooling at the same time that you're seeing increases in the highest temperatures during the day. That's something that you see in California, globally, definitely the case. Relevant to orchards, also, California is just starting to bring online the consideration of land in its climate policy towards the next re-upping towards 2030. And there's some pretty compelling connections there with what happens in terms of what do you do with the cuttings, or what do you do with keeping that carbon on the land for the long haul. That's also relevant pretty strongly in rural areas.
All right, thanks.
Thank you for being here. First off. I'm wondering about the funding that goes into climate science. I think we read studies and we quote things and we hear from climate scientists, but is there a future of funding and new scientists coming into it? Like as somebody who, like, you know, I'm sure you write grants and you operate with people in studies, like do things look good in the future? Like, will there be resources to do studies? And where do you get those resources from right now?
I see a lot of job ads these days for new hires around sea level rise protection. I think some of these things are increasingly going to be necessary as societies are figuring out how to grapple with impacts unfolding in real time, going beyond the fact that we have designed our systems for stasis and stability, and now are really required to move rapidly, not just in the case of decarbonizing our energy system, but also in terms of preparing for responses. Funding for climate change science comes from really diverse sources. There's a fair amount of funding that is from the federal government in origin, whether that's NSF or DOE or EPA. I think it's been interesting to watch that go up and down in terms of the political dynamics. That's more pronounced for DOE, for example, as compared to something like NSF funding. There's also a lot of funding of climate change research that comes from the foundation space, Packard, for example, Hewlett Foundation. And then there's also some funding that comes from industry. And there's some really interesting questions of, you know, are there funder effects? We know they exist in medicine, for example, and there's been a lot of questioning of what does it mean to have funding that comes from the large oil and gas giants to produce transformative change in research on campus. So at Stanford, for example, there's been a major effort over the last decade plus that is called the Global Climate and Energy Project. Huge funding from industry, bringing a lot of industry on campus in collaboration with science, a whole bunch of new faculty lines that were created, really transforming how energy research happens on campus. And that was associated with really clear rules of separation between requirements being implicitly translated to scientists and really keeping the best of those interactions there, but not having specific ties or influences.
Gotcha. Cool. Thank you.
Yes. Again, I'd like to appreciate your presentation, especially at the beginning, this question of attribution. And I guess I have another question about how to communicate this best to a kind of general audience.
Into the microphone.
Sorry, yes, I have a question about how to communicate the sort of causality, attribution of these extreme climate events. You know, I think, well, I'm a sort of scientist, technical, I think quite a few of us are specialists, but not all of us. How do you have a sense of how to communicate to a general audience, you know, when they ask, you know, was this caused by climate change? And the answer obviously is a probabilistic one. Do you have any advice on how to talk about that?
So I can give you the answer that I've been repeating again and again and again around Harvey. So for something like Harvey, where the immediate question is this climate change? The answer I have given is that there's some simple ways to think about how a changing climate drives up risk. So a warmer ocean drives the formation of more powerful storms. A warmer atmosphere can hold more water. With sea level rise, those waves striking on shore are about 8 inches higher in terms of the damages they can cause. I still think that's somewhat technical, but it's a little bit further removed from pointing to graphs and trying to describe what's happening to a fraction of attributable risk.
Thank you.
Another appreciation for your incredibly concise and informative answers, so thank you. Wanted to ask you, I think you used the term atmospheric blocking, which I've heard in relation to Hurricane Harvey, and you sort of alluded to climate change impacts there, which I haven't really heard of before. Can you speak a little bit about how climate change could be impacting that type of atmospheric blocking going forward, please?
Great. So with the caveat that I'm not an atmospheric dynamicist, and this is really complicated stuff, I'll give the simple answer. So basically there are atmospheric patterns that really shape where the movement of energy happens in our climate system overall. So for example, there's this thing during the drought called the ridiculously resilient ridge high pressure system off the coast of California and heading north that meant that storms heading towards California were being diverted and the state ended up being very, very dry. Same thing with Harvey. Basically that storm got stuck there. It couldn't move out of the way, and that had to do with the patterns of pressure in the atmosphere. So in terms of single event attribution, that's in the ingredient or component category, not looking at the event overall. There's been a ton of work that's saying, how do we understand the likelihood of different atmospheric patterns happening with climate change or without? Whoever asked the question in terms of temperature coming down towards Arctic cold coming down to New England, that's the same type of question there, even though I would say the science is still quite open on that one in particular. So you're basically running the model with emissions, without emissions, and saying what types of atmospheric patterns are happening with what type of probability.
Gotcha. So it's sort of more of a question of where we don't have a clear explanation. It's one of those complex things that we don't have a clear explanation, but we are observing it more frequently.
I am sure someone who could write out the equations of conservation of mass momentum and energy in that circumstance could have a more precise answer. Cool. But in terms of the single event attribution, they usually basically publish all these maps of the different types of patterns you get, how frequent the different patterns are with emissions of heat-trapping gases versus a world without.
Got it. Thank you.
And I could point you to some atmospheric dynamicists who could get you a better answer to the specifics.
Yeah, my question is about forecasting for extreme heat and wildfires in California. It's just pretty specific. This year there was a lot of days in the Central Valley over 110 degrees. That seemed like a lot to me. And obviously the wildfires this fall were huge. I think record level wildfires. What are we in for in California over the next 10 years? Those two things specifically.
Okay, so wildfire is a complex extreme. It's not just, is there fuel there or not, which is contingent on the growing season the year before that, dependent on what type of ecosystem you're in. So number one, is there fuel? Number two, is the weather conducive to fire? Is it hot and is it dry? And number three, is there ignition, where that ignition can come from natural or anthropogenic sources. Then in terms of the damages, there's the question of what has the history of wildfire management been? Has management contributed to a buildup of fuels? And then number two, what is the development pattern been? Is there stuff at risk that very strongly interacts with how wildfires are managed? Given all of that complexity, you can still do this type of, is this climate change type of analysis, and it's been done for the American West overall. A paper that came out about a year ago or so found a very substantial increase in fire risk across the American West, similar to the drought study, where it's really a story of it's hotter and it's drier overall across the American risk. And despite the fact that wildfire is incredibly complex across everything I just walked through, the fact that it is hotter and drier overall in aggregate has driven up the risk in a really clear way. In the state of California, into this next decade, I feel like there's some really important questions. So number one, as the state is trying to figure out carbon balance, just from a climate change perspective, forgetting about people on the ground in the moment, we'll come back to that essential category next. Just from a carbon balance perspective, fire is really important in the state of California. There have just been these first few inventories of how much carbon do we have in our forests, and we're finding that that carbon is being lost into the atmosphere due to increases in risk. And I think just kind of existentially, there's this really interesting question of, will transitions of museum ecosystems that were designed for a past climate but just hanging in there, really be stimulated in terms of their transformations to new ecosystems through disturbances like fire? In the state overall, the question of adaptation in the wildfire context is absolutely of critical importance. So how do you prepare for increases in risk that are already happening, that will be exacerbated into the future? There are questions of what the different options are. So for example, should we be doing more things like prescribed burning, getting rid of the fuel that can easily ignite? How do we think about utilities and the way our current liability system works? Profoundly important questions around adapting to that changing risk that is very, very exciting. And I just started working with a PhD student this year where she came in at the start, wanted to do wildfire adaptation, and she has now been obsessed by the literature given the real-time relevance that's just been rather uncanny.
I'm on a committee charged with recommending research on adaptation to climate change for transportation. And I want to know, how do we get from the scientists that extreme end of the curve, what's going to be likely over the next 20 to 30 years? Because we're developing proposals for funding agencies like Caltrans to fund research on facilities, operations, even where people are going to be able to live over the next 20 to 30 years.
I think an interesting thing about transportation is that there's such a strong interconnection between mitigation, reducing our emissions, and adaptation, preparing for impacts. Why is that the case? So first of all, 40% of our state emissions are now in transportation. We've done a great job so far of decarbonizing electricity supply, leaving us with the big challenge of cars, essentially, and long-distance trucking. Also, the adaptation mitigation connection is really, really strong in terms of development patterns. And they're development patterns that can be very adaptive at the same time that they reduce emissions associated with commutes, for example. In terms of just climate change adaptation, preparing for impacts in the pipeline, it's things like temperature of the roads that actually, in many ways, affects their resilience through time. And there are places now in California, but especially on the eastern seaboard, that are flooding regularly. And this is infrastructure that wasn't designed to be flooded all the time. Really questions about the integrity of it and buckling of roads that we're getting as a result. Also in terms of sea level rise, things like bridges, roads are very vulnerable, and they're really important choices when we're putting things in the first time. The marginal cost of climate proofing a new investment in infrastructure associated with transportation is much smaller than a whole retrofit. So kind of those points of rebuilding are really clear entry points. At the same time that there are interesting adaptation mitigation connections that also arise around air pollution, and the fact that, for example, due to wildfires, we've been exacerbating some of our challenges around air pollution in the state, and enters transportation in terms of thinking about some of those interconnects again. Which risk numbers?
Well, probability of extreme heat, probability of storm surge, all that, how's that going to increase? I mean, should we maintain SFO, for example, as a facility? What about our freeways here in Bay? Those are all risks.
So you might check out the process currently underway for the California assessment. So there's a national climate assessment that will have regionally specific information, especially in the next round. But there's also pretty good information through CalAdapt and this assessment that really tried to drill down to regionally specific decision support information.
Hi, two questions. First, just broad brush. Used to think that precipitation in California, generally north of Sacramento, was going to be average to slightly greater than average as temperatures went up. Central and Southern California, probably drier based on the paleo record and most modeling, but I've seen a lot more variability in the modeling as far as how much precipitation we're supposed to get as temperatures go up. What's the latest? Where do you think it's headed as far as precipitation distribution statewide?
Great. So you're exactly right that precipitation, not just in California, but in many different places, is noisy, and it's really hard to tease out the long-term trends. I think some of the basics you essentially laid out, An interesting dimension is how changes in temperature are intersecting with precipitation for snowpack is a really fascinating interconnect, where if more of the precipitation is falling as rain as compared to snow, and it's falling at warmer temperatures once it hits the ground, you're basically getting a much larger runoff. So that affects water resources in the state in a really profound way, even though it's not just straight just straight precipitation. It's again how they're interacting. The questions of drought in Southern California and the Southwest overall are really important, and I'm sure you've looked at the things of mega droughts through time in the Southwest and what's the probability of their recurrence. Again, that's research that's in the space of low probability, high consequences, high uncertainties, but incredibly important. There are some things I could probably point you to in terms of the most recent numbers, but I would still say that the bottom line usually is that precipitation is much harder in California to say there has been a trend as compared to temperature.
Okay, and one more question. When you look at things today, you and your colleagues, and you look at events and you're looking at the statistics compared to, say, what the understanding was 10 years ago, is there anything that's surprising you that's accelerating or going out of bounds more than you would have expected?
Good question. So let's see. I mean, I think the Arctic sea ice decline has outpaced model projections in some interesting ways. Exactly why that has occurred is complex. So partly, data records in the Arctic are poor, not surprisingly. There haven't been temperature stations there through history. So inferring exactly what temperatures have been in the past, how rapidly they've changed, has been part of the big to-do of exactly readjusting the temperature record. I don't know if any of you have followed that over the last year or two. If you say, at the very subtle margin, how much has it warmed to date? The uncertainties in the Arctic are part of the biggest uncertainty, recognizing that they're very, very small scale adjustments. But the basic idea is that as sea ice melts, you're going from white to dark surface, you get a polar amplification, really profound, with interesting questions of how that's playing into regional climate more broadly. That would certainly be a place where there's been substantial advances. I mean, I think some of the interesting aspects have also just been how persistent some of the really persistent uncertainties have been. So about a decade ago, 2007 IPCC assessment report, there was a major blooper in assessment around what happened with the reported numbers for sea level rise. It was an understandable blooper. At that point in time, the satellite record was long enough and the on-the-ground measurements were good enough that it became really obvious that the ice sheets on Earth, Antarctica, Greenland, were flowing a lot faster than models could account for. This basic idea that the major ice sheets melt at the surface, but most critically they flow. And in the West Antarctic in particular, there is the potential for instability or collapse due to that flow proceeding across a bedrock that declines across the water, away from the water. So if we were to say, how has that advanced? There has been major attention to figuring out what are the processes of ice sheet collapse, at the same time that all of this effort has basically still put us in a position where we understand how much sea level rise can happen in the next few decades, but even in the second half of the century, there are massive uncertainties about what we know unfolds in glacial to interglacial cycles very clearly, how rapidly that could be accelerated when we do the same thing with the forcings over a century time frame.
Last question.
Thank you. This isn't so much a question, although there might be one embedded in it, but a quick comment. Katharine, I know you're from Stanford. We've met before. We do a lot of work on behavior change around climate. And we're having an enormous class on May 17th in partnership with the city of Palo Alto for helping people adopt electric vehicles, which is, as you pointed out, the 40%, you know. And we also do lots of work with helping people bike and use transit more. So I just do you have any thoughts about just connecting this more with people's behavior change?
Yes, there are a lot of people at Stanford working at that, and I think it's really making it something that's about opportunity and things people are excited to, and excited to do and not have it be something they feel forced to. And I think people tend to engage with the climate issue when it feels immediate, positive, good for them. And it feels like the great thing around electric vehicles is they're getting way cheaper, and we also have cars that people really love and like, and it's just such a right point for pushing that forward. I think an interesting thing for Palo Alto is that high-income communities have been benefiting from relevant subsidies and adopting faster. What does it mean for all of Palo Alto to have that? And that really feels like it's an opportunity for transformational change in a pretty profound way.
Thank you.
And good bike lanes and infrastructure also would be great.
Working on that too.
Well, we're at the end of our time period, and I want to congratulate, first of all, the audience. I didn't get to any of my questions, and Dr. Mach said they're pretty good questions. But in any case, I hope you can share with me the sense that this particular session was mesmerizing. And I want to thank Dr. Mach for coming and visiting with us, and I want to thank you. So,
Thank you.